Data structures revisited. In this nugget, we're going to introduce a new data type for you called the set. This enables us to take collections of distinct items and perform operations on these. It can be helpful, for instance, for combining two or more lists, removing duplicates, and the like. I think you'll like sets, especially now that we've fully covered the list and the dictionary and the tuple and the string and the number, all the previous types thus far. In the second half of this nugget, we're going to revisit the list in particular. I'm going to show you how we can use a shorthand notation called a list comprehension in order to iterate and perform options on all elements in the list. It's really, again, quite a cool technology. Without any further ado, you know the drill. Let's get to work. So what are sets? If you're a math nerd like me, then you've probably worked with sets at some point in your education or your professional life. In mathematics, a set is defined as a collection of distinct objects that's considered as a discrete object itself. If you've ever seen or heard of Venn diagrams, these are used in mathematics. Interestingly enough, Venn diagrams are also used in psychology. And this one here shows a Venn diagram with two sets, A and B. And you'll note that there's an intersection point where some members of set A are the same as members of set B. We could actually pull out that intersection and create a third data object from it. That's one example of many types of set operations that we use in mathematics. The good news is that you can do the same stuff in Python. In Python, a set is a data type, just like a string, just like a float, etc. It's distinct from all of those previous types, though. It's an unordered collection of unique, immutable elements. Now, when you think unordered, you're probably thinking of a dictionary mapping, aren't you? When you're thinking of immutability, you're thinking of probably the string and the number data types. Again, the set is not a sequence, it's not a string list or a tuple, nor is it a mapping, although really, of these previous types, I would say that the set has most in common with a dictionary. Because sets are not indexed how we normally do it, position 0, 1, 2, and so on, Python does create hash values of each member in the set in order to keep track of them. Defining a set is pretty easy. You'll notice my two examples here. We can create a name, I'm calling it my set, and then using the set built-in function and passing in this case you'll note I'm passing in a string, but we can also pass in a list or even a name that represents another data object. Let me show you how that works. To begin, from the Python interpreter, we'll define a set called S1. Again, I'll use the set function, and you'll note that the tooltip help tells us that the set function takes an iterable, some object that can be run through one member at a time. So in this case, we could certainly insert a string. Well, before that, actually, why don't I do a list? There we are. And if we check the type of S1, of course, we should see that the class or the type is a set. We'll create another set now. This time we will use a string for our input. And I want you to see something here. First, let me echo back the value of S1. Now, it comes back here with dictionary type notation with the brace. And you'll note that it comes back 0246. Now, I don't want to call that a coincidence, but I do want to remind you yet again that the set relies upon hashes to figure out the position of each element, and there's no indexed order like there is, say, with lists and tuples. So you'll find this especially obvious when I echo back S2. The source string for that was CBT nuggets, but you'll note that the resulting set object for S2 lists all of those letters as discrete members, but they're certainly out of order. You see what I mean? To continue this, let's create a set 3 that contains a list that contains, in turn, 10, 12, 14, 16 integer values. And I'll show you a couple of the methods that we can operate upon sets. So for instance, we could do a set1 dot, remember dot notation to access our built-in methods. The methods that are associated with sets are pretty rich and robust actually. If we use the update method, this will allow us to update a set with the union of itself and others. Now, in terms of set notation, intersection gathers the common members between two sets. When we're doing update, we're performing a union where we're taking the entire target set. In this case, why don't I do an update with S3, the one I just made? And if I echo back S1 now, you'll note that we've unioned the original members of S1, 0246, to set 3, 10, 12, 14, 16. Now, of course, you're thinking to yourself, wow, I thought that set members are immutable. That's true. What we're simply doing is taking the S1 name and redirecting it to a new object in memory, okay? I also want you to see that when you create a set, I'll call this new set, you can run the set operation not just on a specific string, not just on a specific list, but you can also bring in other objects as arguments. So I brought in S1 there, and if I echo back new set, I've essentially duplicated the S1 set under a new name. Now, what you've seen me do just now is I've run a function that we haven't talked about yet, but it's really useful, I think, for going into a deeper understanding of the Python programming language, and that is the ID function. If you run ID against a name, what you'll get is the memory address of that object. This can be really useful to prove, for instance, that two names are pointing to the same or different data objects. So you'll note that S1 exists in memory at this location, 63904. New set, which takes S1's value, attaches it to a new name, is a discrete object in memory. Now things can get funky with these references. You'll remember that Python uses what's called garbage collection to get rid of old names and old data objects when they're no longer being referred to. Now check this out. How about we echo back S1, and just for grins, I'm going to choose SX as a new name and point it toward S1. So if we ID S1 again, we get 63904. If we ID SX, you'll note that it points to the very same location in memory. So now let's operate on SX for a minute. I'll show you a couple more methods, and we'll understand yet a bit more about how references work with names and data objects. Another method that's kind of cool, we'll run it on SX now, is the pop method. Now, if you want to remove elements from a set, you can use either pop or remove. Pop is weird because it removes an arbitrary set element. So you don't choose. It's almost like a guessing game or a whack-a-mole game or a bingo game or something. Watch what happens when I run SX pop. Let me say SX equals SX pop. Now, if I run SX again, well, that wasn't exactly what I wanted. By using the SX equals notation, I rebound that name, and therefore if we do an ID on SX, we see that the SX now has a different location in memory. Nuts. Well, why don't we try pop again, this time working with S1. We'll say S1 pop, and it comes back with the element that it struck away. Now, in my experience, it tends to take the first element in the list, but officially according to the Python documentation, pop removes an arbitrary list element, so you want to be careful. So if I bring back S1, you'll note that 2 is now gone. Now, S1.remove enables us to remove a discrete element, and we have to provide it with a specific ID. That is, if we want to remove 10, we can do that, and now you'll note 10 is gone. Next, let's test for membership. I'll echo back S1 again. And although it's very obvious to us what the members of the S1 set are, I do want to show you the syntax just to make sure you know how it works in your code. So if we did an A in S1, the Boolean result is going to be false. Of course, if we choose 6 in S1, then that comes back to true. Remember that in also works in reverse. We could say 12 not in S1. Of course, that's false. But if we did 13 not in S1, that comes back true. That works especially nice in your Python programs when you're doing conditional logic, for instance, with an if, elif, else block. Finally, just for grins, let's clear out everything in S1. We can do an S1 dot clear with no arguments to just give us a bare set. I want you to know I haven't really focused on this too much, that many times in your programming you'll want to define an empty set or an empty list. So you might say EL equals just open and close square brackets, and then if we type EL, we can verify that it's a list. We can do the same thing with any collection type, and then using, for instance, append, or depending upon what we have available for each type, remember duck typing, we would use the appropriate method to begin to add to that collection object. Just wanted to give you a heads up on that. Now, more about sets. I've put together some general thoughts on sets that I think are useful for us. Sets are often referred to in Python as valueless dictionaries. You'll remember a dictionary is called a mapping type, where you're mapping a hashed key to a particular value. Well, I told you that sets do involve hash members, so in a sense, a set can be looked at as a keys-only dictionary type. I haven't shown you this yet. Hang on just a second and I'll show you how it works. But a really nice thing we can do with sets is isolate uniques, because remember, sets require that each member in that collection be unique. That deals with mutability, because if we were to change the ID, the memory ID of an item in the set list, then that item or element would compute to a new hash value, and Python would not be able to reliably track the location of each element in that object. Set operations in Python work pretty much exactly the way they do in mathematics. We've looked at union, where we take one list, for instance, or one iterable, and blend it one-to-one, just the whole kit and caboodle, into a single set. Intersection is where you can take common items from each and blend them. Difference is just the opposite, where we're taking the items that are unique on each side in each list, let's say, and creating a new object from them. We can also do membership testing. I showed you the in and not in, but this is pretty cool too. You can do is subset or is superset. Remember, we used the update set method to take one list and add it to another. So in that case, we had set1 and set2. We did a set1.update, and S1 became a superset encompassing its members as well as S2's members. Let's get back to the interpreter and do some more work. Just to make sure we're starting from a clean slate, we're getting rid of all of our references, all of our objects and memory locations. I'm going to restart the shell. And how we'll begin is I'll define a new S1 as an empty set. Remember, I told you that it's really useful in programming, in Python programming, to start with an empty collection and then add to it as your program needs dictate. So if I do an S1 equals set empty, we can then start populating it in various ways. One way this allows addition of one member at a time would be to use the add method. So by using the add function, we can add one member at a time. This can get a little bit tedious, of course. I'll just add one now. Echo back S1. Might be easier to do this. And then use, of course, update to give us a much more robust set now. Now let's look at looking for duplicates. We're going to start with a long list of representative programming languages, and I want you to see that this source list does contain some dupes. You'll note that Python is in here a couple times, and Ruby is in here a couple times. So let's create a new object called L1 that makes a set out of the language list. And if we echo back L1, you'll notice that those items are alphabetized. Well, no, they're not. I thought they were alphabetized. Remember, unordered. But you'll note that the dupes are automatically gone. Now let's create a second list called Morlang. And I want you to see, you'll notice that Perl is in the Morlang list. It's also in the Lang list. Let's create a set called L2 out of the Morlang list. Now we have L1 and L2. This is a setup to show us some set operations. Remember, difference takes elements that aren't in the other list. That is, if we do an L1 minus L2. This shows us the elements in language that aren't in Morlang. And of course, that's going to be everything but Perl, isn't it? We can also call intersection. I'll start with L1 and intersect with L2. This is going to give us back any elements that are shared by either list. Of course, it's again Perl. Finally, if we want everything, the whole shebang, there's a couple different ways we can do it. I showed you the update, but you can also do this. Call the union method. It gives us everything, again, with no repeats. It's type U, and of course that's a set. We can iterate through sets just like any other iterable collection. For instance, remember the for loop construct. We can easily iterate through each member of L1, writing a simple for statement that looks something like this. We could simply say for I in L1, print I. No big surprises there, I'm sure. Next, let's look at the is subset method. And this is another membership testing type. What you see, I've recreated S1, our first set, 0, 2, 4, 6. S2 is our second set, 10, 12, 14, 16. And I'm just about ready to run the update method in order to append S2's information to S1. Guess I just did it, right? Now, as far as testing membership is concerned, it's really quite easy. We simply say S1 is subset of S2. Is that true or false? Does S1 exist as a subset of S2's data? Nah, we know that that's false. However, if we do S2 is subset of S1, we know that that's correct because S2's collection is now part of S1's. I'm going to finish up this demo by hinting at what we'll be covering next in this nugget. We're going to talk about list comps next, but first I want you to see that we can also do set comprehensions. The only difference between a set comprehension and a list comprehension is that a set comprehension returns a set object instead of a list one. Now I am letting the cat out of the bag a little bit earlier. I'm diving right in. How this works, let me show you the code first and we'll understand it second, is we can start with an iterable collection. I'm using S2, which we know is a set. And if we want to iterate or perform some option on every element in that collection, we can do a set comprehension. So I'm going to define a name called setComp. And mainly the thing that differentiates a set comp and a list comp besides the output is the way we do the actual terminating characters. Here with set comprehension, we use the brace. And if you're comfortable with using the for loop, you're already set as far as this goes. Now this simple set comprehension is going to go through S2 and multiply each member by 2. So we choose an arbitrary name. I, J, K, L are the typical ones used in computer science. So I'll use that here. I times 2. And then in one line, for I in, and then your collection object. Isn't that easy? So if I echo back setComp and check its type, I see that it is a set, so therefore these are unordered. But you should notice that each member of S2 has been doubled. That's a set comprehension. Now with that, now let's turn to list comprehensions and dive in even more what this means. List comprehensions, also called list comps. What these are, friends, are simply a nifty shorthand method for creating new lists. What I just showed you is a variation of the list comprehension, the set comprehension. That's a shorthand for creating new sets. Lists tend to be based on their mutable nature and the fact that they're indexed. Easier for folks to use in most cases. Now, if you wanted to iterate or perform some action on one list and bring that over into a new list, or alternatively just redefine the original list, remember lists are mutable, you have a choice here. We could run a traditional for loop construct, or we can use just a single line statement. It's up to you on how you want to do this. Down here is the list comprehension. Up above we have a more traditional, longer way to go. So in this upper example, we're starting with a name called myList that is in fact a list of mixed case elements. We're then defining our target list, T, as just an empty list to start with. Third, we run a for loop for each member in myList and run the append function on those strings to make them lowercase. Finally, we port or repoint myList to T. Now that'll work all day long. But check out the list comprehension way to go and see how much more compact it is. Here we're saying my list is, we're redefining the name. And then instead of the braces that we saw with a set comprehension, we use square brackets. X.lower for X in my list, which still exists up here. I mean, you can't beat that. List comprehensions are related to another function in Python called map. Map is also very cool. I'm going to show you this in the demo just so it's not unknown to you. Map is neat because instead of iterating a procedure, or in particular a method over a list, or in set comprehensions over a set, map allows you to iterate an entire function over a list. Isn't that awesome? Let's get back into the interpreter and I'll show you what's up. Okay, to start off with our list comprehensions, I'm going to do basically the same thing I just showed you a couple minutes ago with sets, but showing you the specific syntax for a list comprehension. I'm giving just a simple list called a list that generates or has a bunch of numbers in it. Now I'm going to redefine a list by doing a duplication operation. I times 2. Let's just do 4 this time to give us some variety. For I in a list. Of course, a list is a list, and if we echo it back, we now see each member of that list multiplied by 4. No big surprise. Next, I've created a name called phrase, which is pretty long. You've probably seen the boilerplate text lorem ipsum before. It's useful for just putting in dummy placeholder text. Just as an aside, I'll tell you there's a site I've used over the years, probably hundreds of times, called lipsum.com. It's a lorem ipsum boilerplate text generator. At any rate, I've got this fairly long string, and you notice that I've invoked the split method on it. Now, what's that going to do? First, let's check the type. Now, you'll note that split comes back with a list. So we started with phrase being a simple string, but split created a list. Let's now echo back phrase. And the split gives us a list with each word a separate member in that list. You with me so far? Now what we can do is perform some formatting list comprehension on the phrase list. Let me show you what I mean. We're going to define this or capture this in another name. I'll call it stuff. And you might accuse me of kicking up the complexity a bit too much in this example, but I got a little too excited, I guess. And what we're doing here is, you'll notice we've got an internal list where we take the iterator, P, that's going to run through each member of our phrase list, and it's first going to give us uppercase representation, then it's going to give us a lowercase representation, and then it's going to give us the string length for P in the phrase list. That's our list comprehension in a nutshell. So if we echo back stuff, you'll note that we get a list of lists. This internal list has 3 members, uppercase, lowercase, and length, and then again the P iterator hits each word in the phrase list. Pretty sophisticated stuff, isn't it? Now, if you didn't think that we had enough in terms of comprehensions with just lists and sets, the next example shows us how to do comprehensions with dictionary or associative mapping objects. Now, I've created a dictionary called Dic1 that has 3 keys, A, B, and C, in words, and then the values are 1, 2, and 3. Now, if for whatever reason we needed to swap those values and those keys, we could run a comprehension on the dictionary. You'll note the dictionaries also use the brace terminal character just like the set comprehension does. And what we do is we specify our operation. In this case, instead of key colon value that's normally done in a dictionary, we're going to say value colon key for key comma value in our dictionary. Now the words here, the names are important. Remember, key and value are reserved in Python because keys and values in dictionaries go by those names. So the syntax here is a little bit different than what you'd expect. We're doing our operation on discrete elements in the dictionary, and then to get into the dictionary proper and hit each item, you'll remember that dictionaries have many methods. This is the one we want here, items. Items affects both the key and the value. We bring back dic2, and it has effectively swapped the keys and the values for us. I think you'll like this next example. We've flirted around with the open function a bit. We have yet to formally define it. That's covered in an upcoming nugget. But for now, what we're going to do is we'll try to create a list out of lines in a simple text file. Now this could be a script file, a log file. In our simple case here, we work with simple cases when we're getting started, is a text file I've created called lang.txt in the root of drive C. And as you see, this is nothing other than a single column list of programming language names. Now I'm defining a name called lang, and I'm calling the open function and passing in the fully qualified path to that file. Now in Python 3 you might get some strange results here. You notice that I don't get the contents of the file if I do a straight open. So what I'm going to want to do, I'll come up to the line, hit enter to get it back. I'm going to need to convert this object into a list discretely by wrapping the open function in the list function. Verify that we have a list, and then let's bring it back. Now you'll notice that we have our new lines. After all, in the source text file I pressed enter after each name. How can we get rid of those and clean up this list? Well, an easy way to do that actually is a list comprehension. So what I'll do is say that lang is equal to, I'll just call the name or variable n, and I'll call rstrip to get rid of those new lines for n in the lang list. That makes sense? Now we've got a really nice list, a cleaned up list that we pulled from an external text file. I hope your brain's not hurting. 2 more examples, then we're done, I promise. This first one wraps up a lot of what we've learned thus far and includes some list comprehension stuff. The second script file I created for you is going to demonstrate the map command. Alright, so what's going on in this mod9.py file? First thing, you'll notice that even though we're on Windows, we don't need this line. I'm including the exec hack line for a couple reasons, to remind you that this is what we use in NIC systems to be able to run a script file without having to locate the Python interpreter if it, for whatever reason, isn't already in your search path. The second reason I've included this is so you're not surprised when you see references to the hash and the exclamation mark called a hashbang or a shebang. Now you can go search online for the etymology of that at your leisure. I just want to make sure that you come out of this training with as much programming speak under your belt as possible. Alrighty then. All right, so what this is going to do, first I'm declaring, now is S a local or a global name? I guess with this comment, gee, I'm mad at myself. Let me get rid of that. I already let the cat out of the bag. Remember when we talked about functions? We talked about variable scope. That is, within a function, and there's our def statement. It looks like we're declaring 4 of them, one right after the other. Whenever we declare names within a function block, or within, say, a class definition, those variable names exist only within that block, so it's local to the function. If, however, in our module file, we want a name to be globally accessible, the best way to do that, I've found, is to declare them outside of any subroutine. All right? So you see I've declared a name called uppercase S, and what this does, we know what the star is, right? That's exponentiation. It will exponentiate an integer in the range with max 10. Now, what does that give us functionally? How many? Gives us 0 through 9, doesn't it? Remember that range does not include the topmost member. So this is a good example, actually, of a list comprehension that uses the built-in range function as its collection instead of a discrete dictionary, set, list, or string. Okay? Now, let me bypass these function definitions just for a moment, because what's happening is when we run this script, we're going to be hit with some formatted text. Which operation do you want to perform? We can choose A to do an x to the second power, B 2 to the xth power, C we can do a division, what's called modulo division, mod 2, or D to quit the program. That's going to be the user interface that the user is presented with. And you notice that I'm using some techniques that we've already learned. We can embed new lines to give ourselves some blank or white space between paragraphs. We can use the triple quoted string to give us more formatting. You'll note here we're presenting kind of a multiple choice motif. And then we're running 2 input statements and capturing those to names, resp and resp2. First, we're going to have our choice where we're expecting A, B, C, or D. Input returns a string, so we don't need to worry about formatting it. Next question is, we need to choose an upper limit. In other words, if we're going to do x to the second power, how many iterations do we want? Do we want to see x to the second power up to 10, up to 20, etc.? And we need to reformat that as integer in order to get a numeric value. Next, we have our conditional logic. Depending upon what the user presses, if resp equals A, we do this. If they do B, we do this. If they do C, we do this. Else would be if they do anything other than hit A, B, or C. Specifically, we want them to hit D to quit. We do choice D. Now, you should notice how compact this if block is. It's compact because you'll notice that I'm embedding function calls. To give a good demonstration here of what we've learned, we know that in true procedure-based programming, we're relying upon modular units called functions that can make our code easier to maintain over time. And you'll note that this if block is a lot easier to understand too, because we don't have specific lines of code in between each of these choices. We are, for instance, calling the choice A function and passing in the resp2 name as an argument or as an input parameter. Choice B, again, resp2 gets passed into it. C, resp2 gets passed into it as an argument. And the choice D function evidently does not include any input parameters. You see? Now, the functions need to be declared near the top of the file because remember, the Python interpreter is going to start at the top and then go line by line. If we do our if block and our inputs before our functions, then you're going to wind up having Python get confused because it's being asked to run a particular function when it hasn't yet reached that in the file. So you notice that we have 4 function declarations, choice A, choice B, choice C, and choice D. All choice A does is print the value of S. So that's the power of 2 option, and that's up here. And by all that's right, I should modularize this instead of hard coding it to 10. But for now, just for the sake of example, I'll leave it alone. If someone chooses choice B, that's 2 to the power of I. We're first declaring a name called V that takes 2 to the power of I for the range X. And you notice that X in this case is that input parameter. In other words, upper limit 10, then we're going to do 2 to the 1, 2 to the 2, 2 to the 3, all the way up to 2 to the 10. We're going to print that value and then exit the function. Choice C is the modulo, where in the declaration we're doing 1 input parameter. Here, just to demonstrate that we don't have to have the same letter. This is really arbitrary. Remember what I said about local names. They exist only in the block. I'm calling this input or this argument Y, And a minor edit here to fix a mistake. We're bringing in range to the y in our modulo expression, and then we're printing out that name. And then finally, if the user chooses D, we're going to raise a call to system exit to exit the program. Let's now run the module, and we get our first line. Which operation do you want to perform? A, B, C, or D? We choose A, gives us our upper limit, I'll say 10, and then it runs x to the second power up to the power of 10. The final thing I want to show you in this nugget is the map function. And as previously discussed, map allows us to iterate a function over an iterable collection. So in this script file, I'm defining a function called mult that takes one parameter called val, and it's returning val times 2. Very simple case. As far as applying that function in our code, we're doing a list, then another name called iter that calls the map function. And the way map works is we first put the name of the function, comma, and then the iterable collection over which we want the function to hit. It's simple as that. The thing that's not so simple that you need to remember is that similar to how in our earlier example we had to use the list function to make output readable, when we print back our result of the iter name, we're going to have to convert that guy to a list, because in Python 3, the map function returns what's called an iterator object and not a list. In Python 2, map does return a list, and all we would have to do here is do a print space iter. Python 3, we actually have to convert to a list to make it readable. So let's run this module, and we get our results as a list. Data Structures Revisited Review. We're just getting deeper and deeper into this Python stuff, aren't we? Are you still excited? I sure am. We looked at the set object type. We got into a pretty good degree of depth, I think, with what sets are. You now know how to take larger collections of data, remove duplicates, and perform other set-oriented activities. Intersections, differences, unions, etc. Really useful tool to have in your Python programming tool belt. We next looked at list comprehensions, which, to review, is a really nice shorthand method to iterate through all members in a list. I also threw in some extra information and showed you we can do the same thing with sets. Those are called set comprehensions. We can even use the map function to iterate a function over all members of a collection. I hope that this has been informative for you, and I'd like to thank you for viewing.